All right. Well, welcome everybody to this week's Discrete Cat seminar. It is my absolute pleasure to welcome Sara Billey here from the University of Washington. So Sara and I met 2 summers ago in Colombia, doing some nice math and salsa dancing. And I think Sara is an amazing speaker. And so I'm very fortunate that despite all the things that are happening, we are able to have her here virtually. And so Sara will be talking to us about limit laws for Q-hook formulas. So let's welcome Sara.
Well, thank you. Thanks so much for the invitation, guys. I wish I was there in person with you all. Trying times that we're in, but let's talk about math for a little bit. So let me check, actually, do I have until 3 p.m. or is it a little shorter? I'm sorry.
A little bit shorter for questions, and then, but I think it's good if you get close soon.
Okay, let me see how much we can get through. So I want to talk about these limit laws for Q-hook formulas. Actually, the title of the paper we just posted on the archive last week it's a little bit more formal. In fact, it's Moduli spaces of limit laws for Q-hook length formulas. And I want to justify that title to you, sort of at the point of the talk, maybe. This is joint work with Josh Swanson, who is at UCSD right now. He's a postdoc there. He's just been fabulous to work with. I think this is our 5th paper together or something. So the slides are posted on my website with this URL. If you see, hopefully it's posted in the chat too. If you want to download the slides and follow along, feel free. And so here's the overview of the talk. I want to talk to you a little bit about what we've been doing over the last couple of years to sort of warm up the process. We've been looking at standard Young Tableau and the major index statistic and how you can look at the Q enumeration of those things as a random variable over standard Young Tableau. So Andres has seen that part of the talk before, but then we've been getting into more and more generalizations of this. So these are like generalized hook length formulas. And so I want to tell you sort of where we are going with the generalized hook formulas and what specifically is in this new paper. And that's the moduli space of limiting distributions for 2 special cases of Q hook length formulas beyond what is known for standard Young Tableau. That's for semi-standard Young Tableau and for forests. Those were the next more challenging cases. And then there's some open problems along the way. There's definitely room for people to get involved. So I'll point those out. Okay, so the background for this talk is our friend, the standard Young Tableau of a particular partition shape, let's say lambda. And that's just a bijective filling of a bunch of squares like this, where the top row has more squares than the second row, and the second row has more squares than the third row, and so on. So you have a bijective filling of that with the numbers from 1 to n, but they do have to increase as you move to the right and down to be a standard Young Tableau. And an important fact that hopefully everybody has seen before is that the standard Young Tableau of shape lambda index a basis of the irreducible representation of the symmetric group that's indexed by lambda. That's a connection that's very well known and why they came up originally about 100 years ago. And one of the things that I think of is sort of an absolute miracle of combinatorics is, sometimes you can find a formula to count things, and sometimes you just can't find a nice formula to count things at all. But with standard Young Tableau, if you want to count the number of standard Young Tableau of a particular shape, there couldn't be a nicer formula. It's called the hook length formula. It's due to Frame, Robinson, Thrall from the 1950s. And it is just this rational product. So it's n factorial divided by the product of the hook lengths. A hook length of a particular cell in a partition shape is just whatever that box is. You count the number of cells directly to its right, the number of cells below, and the cell in the corner itself too. So those are the hook lengths. In the example down below, I filled this tableau shape not with a standard Young Tableau, but with the hook lengths themselves. So that 7 in the upper left corner is because there are 4 boxes to its right, 2 below, plus the 1 that contains the 7. So that's the hook length. Each of those are the hook lengths. So this formula, okay, it computes instantaneously, even for a partition shape of size like 2000, right? This is really, really very efficient formula. And in this example, where the partition shape has got 5 boxes on the first row, 3 on the second, 1 on the third, so the partition is 5, 3, 1. It's a partition of 9, if you add up the parts. How many standard Young Tableau are there? Well, it'll be 9 factorial divided by the product of all these numbers of hook lengths. So 7 times 5 times 4 times 2 times 4 times 2, and the 1s. So 162. I mean, you could have just computed this by hand, right? This is very easy to calculate. So if you haven't looked at this proof, the proof of the hook length formula before, I highly recommend it. There's lots of different proofs in the literature. My favorite is due to Green, Nienhuis, and Wilf from 1979. That's a probabilistic approach where not only did they give a nice proof of the hook length formula, but they also give you a way to uniformly at random choose a standard Young tableau of a particular shape, which is great for experimentation. All these other proofs have nice properties too, though, so it's worth studying them. And so we were going to talk about Q analogs of the hook length formula. So I want to, instead of just counting standard Young tableau, I want to give you a way of Q counting them, sort of with some statistic in mind. And the statistic that we're going to use in particular is the major index. To define that, I have to tell you what the descent set is for a standard Young tableau. So you have one of these standard Young tableaus, and you just look at all of the numbers. And if I appears in a row that's above I plus 1, we call it a descent. And that would mean that if you were reading along the rows from bottom to top, you would see I plus 1 before you see I. That's equivalent. Okay, so I is in the descent set if and only if I plus 1 is down in a row below it. And then the major index is the sum of the descents. That is the analog of the major index of a permutation, which is also the sum of the descents. But here we're doing this descents over a tableau. So in this example, I now have a T as a standard Young tableau here with 1, 3, 6, 7, 9 across the top. So the descents in this case are in red. 1 is a descent because 2 is in a row below. 3 is a descent because 4 is in a row below. 4 is a descent because 5 is in a row below, but 5 is not a descent, right? Because the 6 is above. Above or to its right would also count. So I guess I don't have an example there where something is exactly directly to the right. But the descents here are 1, 3, 4, and 7. If I add them up, I get 15. So the major index of this tableau is 15. Everybody comfortable with that? Okay, so once we've got this statistic on standard Young tableau, we could add them up into a generating function. So let's use the notation SYT of lambda superscript maj of Q to be the sum over all the standard Young tableau of shape lambda, Q to the major index of that tableau. All right, and how does this relate to the hook length formula? Well, let's take a look at a little bit of data. So if we take that shape 5, 3, 1, and we take the 162 standard Young tableau of that shape and write them all out, what are their major index, and add up Q to that power, you'll get a polynomial that looks like this. Its degree is 23. It doesn't have a constant term, right? It's got zeros down there at the bottom. And you might look for patterns in this sequence. One thing you might notice is that it's symmetric, right? If you look at the first coefficient and the last coefficient that appear, they're the same. And the coefficient of Q to the 22 matches Q to the 6, and so on. Okay, so that's one thing you might do. Another thing you might do is try and factor this, right? What kind of the factors does it have, and so on? Well, believe it or not, it has the most amazing factorization as a rational function. And this is Stanley's Q analog of the hook length formula. So you might want to jot this down on a piece of paper if you haven't seen it before. But the Q analog here is just literally you take the number n factorial and you turn it into a Q analog of the number n factorial by wrapping square brackets around it. So that's the standard analog of n factorial. And it depends on the standard analog of Q analog of the number n. So the Q analog of the number n is the polynomial 1 plus Q squared dot 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 up to Q to the n minus 1. So that's a polynomial that has exactly n terms in the sequence. So if I put in Q equals to 1, I get back the number n. I could also write that as Q to the n minus 1 divided by Q minus 1, right? Okay, so you have the Q analog of the number n, and so the Q analog of the number of the n factorial is just the product of all the Q analogs of n, n minus 1, n minus 2, down to 1. And then in the denominator, you just Q analog all of those hook lengths number, and boom, you've got something that is almost exactly the right generating function. The only thing is that that thing would have constant term 1, but what we saw in the last example was the major index actually had shifted up a little bit. So we have to multiply it by Q to the B lambda. And B lambda is another simple statistic. It's just the sum. If you have a partition written as lambda 1 bigger than or equal to lambda 2, bigger than or equal to lambda 3, and so on, then you just take the sum of I minus 1 times lambda I. That's B lambda. Okay, so this couldn't be nicer, right? This this generating function as this, again, lovely rational generating function. And there's a trick in my mind. So these, if I had to take a big polynomial like this with and the Q analog of n factorial, if I had to multiply that all out and then divide by these factors, it would slow down my computer. But there's a trick to this whole business that I think is just fabulous. And it's really how we got the theorems involved here. And that is that whenever you have Q analogs of numbers like this as your factors in the numerator and denominator, they all factor as irreducible polynomials over the integers into cyclotomic polynomials. Those are the irreducible factors of Q to the n minus 1. And so we can just write each Q analog of n as a product of cyclotomic polynomials. And the formula is just there's exactly one for each divisor of n. Each of the cyclotomic polynomials are indexed by a distinct integer. So all I have then is in the numerator of my standard hook length formula there, we have a multiset of cyclotomic polynomials indexed by positive integers divided by a multiset of cyclotomic polynomials. I take the bottom one and it has to be contained in the numerator, or otherwise I wouldn't have the factorization cancel out and get a polynomial. So you just have multiset minus multiset, and you then multiply out what's left. So I never actually multiply out the numerator. Okay, so that's the trick to these things. And there's some nice corollaries if you look at this Q analog of the hook length formula, one of which you can see is the Q analog of the standard Young tableau of shape lambda are almost exactly the same as what you get when you transpose a partition shape. So that's the conjugate partition. It's only going to be off by a factor that Q to the power is going to be off. So fix that up. And the other thing is that you see from this formula right off the bat, I don't have to prove it to you, but the coefficients are going to be symmetric because of the nature of cyclotomic polynomials. They are symmetric. And actually, I don't know a bijection that proves number 2 explicitly. So could you give me, for every tableau of major index k for lambda, could you find for me the one of complementary MAJ for the same lambda? I don't know how to do that. But another thing that you get out of this polynomial is that the first coefficient was 1 and the last coefficient was 1. So we must have a unique tableau of shape lambda of minimal major index and one of maximal major index. Right? And that's kind of nice. They're bounded in between those two. All right. And why? I mean, I don't know about you, but when I first saw the major index as a statistic, I said, what a weird thing to do, to add up the sum of the descents. Like, what does that mean? That doesn't mean anything to me, right? Well, yeah, do you agree?
Oh, no, sorry. There's a question.
Okay.
I didn't mean to interrupt you. Is there, so Ben asks, is there an algebra for which this polynomial, I think in the previous slide, is the numerator of the Hilbert series for some grading?
Perfect. Ben, your timing's perfect. There it is. So here it is. So the co-invariant algebra is the answer to the question. And this is, to me, is the exact reason why major index is important. So if you take polynomials in n variables and you mod out by the elementary symmetric functions, or think of it as any of the homogeneous polynomials that are invariant under the Sn action on those variables, you get that's the co-invariant algebra. It comes up in the flag manifold, it comes up in representation theory all the time, it comes up in Martha's work, right? It's very important. It comes up in a lot of different ways. So that quotient, because the numerator and the denominator of that quotient both have an Sn action, the quotient has an Sn action. And so you can ask, how does that algebra decompose into irreducibles? And the Sn action respects the degree of the polynomials. So you break it up into different degree pieces. And if you want to know how many times does the irreducible S lambda appear in the polynomials of degree k of this quotient, the number of times is exactly b lambda k, where b lambda k is the coefficient of q to the k in this polynomial. Isn't that nice? I think that's okay, once you see that, you say, okay, major index is important then. And this is a theorem due to Lustig and Stanley, but it has a little bit of a sordid history. So Stanley published it in 1979. In the paper, he doesn't prove it. He says it's unpublished due to Lustig. And Stemridge eventually filled in the details in the literature. So it's clearly true. And people can, if you're good at these things, you can prove it yourself. So it's not a bad exercise if you're good at the SN rep theory. But I think it's just a lovely theorem. Okay, so these coefficients that come up in this polynomial are worth studying. because the covariant algebra is so important. And what we really want to do is ask questions about these numbers on sort of an asymptotic level. So what kind of questions could we ask? Well, first of all, you could ask, where are these coefficients not zero? Those would mean, where does the S lambda irreducible representation appear, or not appear? Just a yes, no question. So that's the first step. Do we understand where the zeros are in this polynomial? And then could we describe the distribution of the coefficients? Do they go up and go down? How large do they get? Could we say something in the limiting process? And a lot of people are interested in unimodality or log concavity and other problems too. So we're certainly interested in the unimodality question. Do they go up and then go down, or do they kind of wiggle along the way? So here's a little more data going back again to the exact one that I showed you before. So is this one unimodal? Does it go up and go down? I see some heads nodding. So yes, this one's unimodal, right? And I'm going to show you a bunch more data. So let me collapse it a little bit. Instead of writing it out as a polynomial, I'm just going to list the coefficients like I did along the bottom there. Okay, so here's maybe too much data for a slide. Digest it for a minute. The first one is for the partition 2, 2. And the coefficients are 1, 0, 1. So not unimodal. Internal zeros, right? So they don't always have increasing and decreasing. 5, 3, 1 we just showed you. 6, 4 is another interesting one. Is it unimodal or not? Wiggles a little there in the middle, right? And then 6, 6 has some internal zeros again. And then, as they get bigger, the coefficients just get a little crazy. And I don't know what you should do when you're looking at that. For the partition 11, 5, 3, 1, that I find a little overwhelming. I don't even think I got them all to fit on the slide. But that's because we're looking at them the wrong way. It starts to look better if you start plotting them when they get so big, And so here's 5, 3, 1 again, but on a plot. You already saw these coefficients. And here is 11, 5, 3, 1. It's easier to parse it like this, isn't it? And what does that curve look like to you? Well, it's a bit of a trick question, right? It's supposed to look a little bit like a normal distribution, but it's not quite right. And you can't tell how far off it is until you really overlay the normal distribution on top of it. And it doesn't quite match in the tails, but it's looking pretty close, right? And here I chose to overlay the normal distribution with the exact same mean and standard deviation, so that it should match up pretty well. And it does, it's getting pretty close. And that's really the theorem we're going for. How often is it that we're approaching a normal distribution with these partitions? But here's another one. I took the partition 8, 8, 7, 6, 5, 5, 5, 2, 2, and write down those coefficients and then plot them, and overlaid the corresponding normal distribution. And just in case you don't believe me that because this one looks like it fits perfectly, right? But maybe I just have dots. But no, in between, you can see the curve really is there, right? So it's fitting perfectly by now, by eye. Okay, so see if I can get that back to normal size. Okay, great. So that's kind of what we want to look at. So let's talk just a little bit briefly about these questions. I don't want to take too much longer on this because I'm still talking about the old work versus the new work, but I wanted to set the stage for where we're going. So the existence question, when does b lambda k equal 0? In previous work that just got published this year, Josh Swanson, Matthias Combinatorics, and I proved that we can completely characterize all of those internal zeros, and they only happen when you have a rectangular shape, and they only happen when you come in one step from those outside ones. And otherwise, you have no internal zeros ever coming up. And we were very happy with this theorem. The way that it worked, I think it's kind of interesting. We ended up imposing a new partial order on standard Young tableau of shape lambda, and it's ranked by the major index, and it's connected all the way up. And that's how we prove that there are no internal zeros except for the rectangles. So we start with the minimal major index tableau. Let's throw away the rectangle cases for a moment. Minimal major index tableau, and then show that you can always get to one with one more match, and you can always get to another one with one more match, and so on, until you step all the way up to the top. And with rectangles, we just throw away the min and match ones and start one step in. But these are different than what we've seen in the literature, like with the Cyclotomic tableau and Majtaskin's work. Poirier, Rattenauer have something, and Hugh Thomas and these other names are harder to pronounce, Kosowski and Schindmeyer, they have another tableau on standard, another partition on standard Young tableau that is interesting, but not quite the same as ours. So we're hoping that people will recognize these in their work somewhere. I don't know, but here I thought I'd show you a couple. And especially since you guys in particular seem to, be interested in the polytope side of life. I don't know if there's something, nobody's really picked up on this yet. This is relatively new, these new Tableaux. We have 2 flavors of the posets for each shape. And what I've drawn here, it doesn't look like Tableau, but these are just the reading words for the standard jug Tableau of the shape 3, 2, 1. And so I don't know if there's an interesting polytope that could go with these posets, but I'd love it if you guys would think about that a little bit. Okay, so just put that out there. So one of the things, the paper ended up getting rather long because we didn't just do this for the symmetric group. We pushed and pushed, and it turned out it just generalized to every next step and next step and next step until we had actually covered the case of all possible Shepard-Todd groups that come from the finite complex reflection groups. And so we can characterize what are called the fake degrees in every single type. When are these coefficients non-zero in their analogs? So it's pretty complete now in terms of that theory. Okay, and what about the distribution question? What can we say about the limiting distribution on the coefficients of the Q analog of the hook length formula? So really now I'm starting to switch from doing combinatorics to doing probability. So transfer over with me. I claim they're actually equivalent points of, just different points of view. So if I have a polynomial with non-negative integer coefficients, I can always make a random variable out of it. And let's say the polynomial is f, I'll call the random variable x sub f. Then the probability that the random variable x sub f is equal to k is just going to be the coefficient of q to the k divided by the sum of all the coefficients. That's some perfectly good probability distribution, right? Discrete distribution. And okay, so if f, our polynomial, happens to sit in the family of polynomials, we can see how they relate to each other. These random variables relate to each other. So if we do this particularly for the Q analog of the hook length formula, I'm going to use those b lambda k integers as the numerator, divide by the total number of standard Young Tableau of shape lambda. That's going to be the probability that the random variable x lambda maj equals k. And the claim that we just saw in the picture is that these random variables are usually approximately normal distributions. But what does that mean, usually approximately? And what does it mean to be a limiting distribution for partitions? Because how do partitions go to infinity? Right? There's a lot of different ways that a partition can go to infinity. Its first row could go to infinity, right? Or the size could go to infinity. They could get super tall. There's lots of different things you might say. So we have to make that more precise. So first of all, I want to point out that in the literature, Ronadine and Yuval Reuschman, 2001, had already put some statistics related to these random variables in the literature. So the mean you can describe right away from the Q analog, the hook length formula. There's 2 different ways of writing it. Let's focus on the second one for a moment. So the mean for a particular lambda is that statistic b lambda that we saw before, plus 1/2 times a pretty interesting sum. It's just the sum of the numbers from 1 to size of lambda minus the sum of the hook lengths. Okay. And the variance actually looks kind of similar to it. That's why I like the second one better. So the variance is 1/12 times the sum of the squares of the numbers from 1 to the size of lambda minus the sum of the squares of the hook lengths. So what do you think the next one up is going to be? Well, we're going to put some cubes in there, right? We're going to put some fourths in there. So that's where we're going. So when we talk about that, just hold that thought for a second. I need to introduce this notation. So the standardization of a random variable is what happens when you just shift the mean to be 0 and then you divide by the standard deviation. So the new random variable just has standard deviation 1, mean 0. Okay. All right. And then I have to tell you about asymptotic normality. What does that mean for a sequence of random variables to be asymptotically normal? It just means that if you look at the associated cumulative distribution functions, when you take the limit on those CDFs, the limiting function is, here I did it with the standard normal distribution with mean 0, variance 1. And we're always looking at asymptotic normality with respect to standardized random variables. So it'll always be mean 0, standard deviation 1. Okay, that's the definition of asymptotic normality. It makes sense. And now here's how partitions can go to infinity. Like, I want to take into account all the different ways that partitions could go into infinity. And the nub, the sort of the most important thing that we decided to pay attention to was a statistic that we think is new in the literature called the aft of a partition. And so the aft of lambda is n minus either lambda 1, the size of the first row, or the size of the first column. So n minus max of lambda 1 or k, whichever is smaller. Okay, so for 5, 3, 1, the aft is 4, because if I take away the top row, I have 4 left. If I took away the top column, I'd have 5 left, but I want the smaller one. So we did add aft to FindStat. And somebody asked me recently, did we add it to the OAIS? And I had to say no, because it's a statistic on partitions, so I didn't know how I was going to add that to the OAIS. But actually this morning I thought of a way to do it, and it looks like it might be more interesting than I realized, but just try to make it into a 2-parameter sequence, like as a generating function. So hopefully we'll add that sometime soon. But anyway, you can find it on FindStat. And then the theorem that Matthias Kombelinka, Josh Swanson, and I worked on, and it's also coming out this year, is that no matter how you take a sequence of partitions and think of the corresponding random variables, then the corresponding sequence of random variables is asymptotically normal if and only if the aft statistic goes to infinity. However, your partitions go to infinity. As long as the aft goes to infinity, the sequence will go to an asymptotic normality and it'll converge. So I thought that's nice. And then what happens if aft doesn't go to infinity? Could you still possibly have convergence? And we completely characterize convergence and distribution. So if aft goes to infinity, you get asymptotic normality. If,
Hey, Sarah.
Yep.
Sorry to interrupt, but so is that like saying that the size of the partition has to grow, but it has to also kind of grow 2-dimensionally? Like it can't be long and skinny? Is that the intuition?
Yeah, basically, right. So if you have a long top row and then just like 3, 2 at the bottom, you won't end up with asymptotic normality.
Okay.
Exactly. Yeah. And then, but you can end up with other things too. There are other continuous distributions that you can end up converging to. And so if aft converges to a constant, but maybe the partitions are not actually converging to a constant, you end up with what's called an Irwin-Hall distribution. And sometimes they're called uniform sum distributions, because this is like taking m copies of the uniform continuous random variable on 0, 1, the interval from 0 to 1, and add them up, and they're independent. So that's the Irwin-Hall distribution. You might end up getting that. That's for exactly like what Ben just said. You have sort of a long first column or first row, and then something that ends up converging down below it. Or the other thing is you might end up with a discrete distribution, because in my sequence of partitions, I might just eventually have the same partition repeated infinitely often after a while. So that's also a possibility. So there's 3 cases of convergence, and that's it. So we were happy because this is like a complete answer. And here, let me show you a little bit of that data. So if you take lambda to be the partition 100, 2, it looks like the distribution, those dots that you see are starting to line up looking like the sum of 2 uniform distributions. And I impose the normal distribution over it to say, clearly it's not normal, it's something else. If you have 100, 2, 1, starting to look a little more like the normal, but that's what you expect, right? Because if you add up a lot of independent, identically distributed random variables, by the central limit theorem, we're going to get normal. But when you have just, this one looks more like just the sum of 3 independent uniform random variables. And even once you get already to 100, 3, 2, so this is like 5 uniform random variables, you're starting to see a pretty close fit. And we know that because the central limit theorem converges pretty fast. But it's not quite right. It really is still just the Irwin-Hall sub 5 distribution that's converging to. All right, so quickly I'm going to tell you a little bit about the proof idea, because we're going to use the same thing in a moment. So you probably heard about the moments of random variables, right? The first moment is the mean, the second moment is the variance, the third moment, and so on, get more interesting. The dth moment is the expected value of the random variable raised to the dth power. That's just the definition. And the moment generating function then of a random variable is just, for us, just put all of those moments into a generating function, an exponential generating function. So the sum ud t to the d over d factorial. Okay, so the moment generating function feels pretty familiar to me as a combinatorialist. And one thing you might do is take the log of that generating function. That gives you another generating function, and look at those coefficients. The coefficients of those things are called the cumulants. They're a little less familiar to people, but I think actually we've been teaching everybody the wrong thing in probability class. The cumulants are the best thing since sliced bread. So the cumulants I'm going to denote by kappa sub d. Okay, those coefficients, and you know how to get them, right? You write down the moments, take the log of that generating function, you grind through the machinery of chapter 5 and EC1, and you get these coefficients. And what's good about cumulants? Well, first of all, the first cumulant is the mean, and the second cumulant is the variance again. Okay, so that's nice. They have a shift invariance property. So if for the second and higher ones, it's like the variance. You don't care if you add a constant to the statistic, it won't change the variance. Same thing holds for all the higher cumulants. The homogeneity property is that if you take if you know the cumulants of a random variable x, then you also can figure out the cumulants of c times x for any constant c. It's just the dth cumulant will be c to the d times kappa d. Okay, so that's easy to pop out a constant. And then additivity, this is the most important property of cumulants that does not hold for moments. So you know how the sum of the expected value of a bunch of random variables is the sum of the expected values? And the same thing holds for the variance. If you have two independent random variables, x and y, then the variance of x plus y is the variance of x plus the variance of y, if they're independent. But the higher moments, that's not true. And for cumulants, it's always true. For all of the dth cumulants, as long as the sum is of independent random variables, the sum of the cumulants is the cumulants of the sum. Okay, and we're talking about Irwin-Hall distributions and such, right? That's what we have sitting around, sums of independent random variables. So the cumulants work perfectly for us. And then there's another thing that's important too, polynomial equivalence. So if you know the moments, you can figure out the cumulants. If you know the cumulants, you can figure out the moments. And for all the distributions that we're talking about, the moments and the cumulants determine the distributions and if and only if. So that's really, we sort of convert the problem from probability back into combinatorics this way. Okay, so here's some familiar examples then. What are the cumulants for the normal distribution? So if you have mean mu and variance sigma squared, then those are the same cumulants, but all the higher cumulants of a normal distribution are all 0. Isn't that nice? I like 0. 0 is my favorite number. And if you look at the moments, they are 0 for the odd numbers, but not 0 for the even numbers. And you know, it's not too bad. You get the double factorial in there. You could write them down, but they're not as nice as 0. And what about the Poisson random variable? That's interesting because it has mean mu, let's say, and then also its variance is mu. Well, it's actually true for all the cumulants. They're all mu. All the higher cumulants are also mu. If you look at the moments, they're not quite the same. Mu sub d is mu sub I times a Stirling number. So you have to do that sum all the way down. Okay, so you agree cumulants are good? We should all know cumulants. Okay, so here's the theorem that comes up with standard Young tableau. If you want to know the dth cumulant of the random variable corresponding to the major index, picking a standard Young tableau uniformly from all of them for a particular shape lambda, the dth cumulant looks just like the mean and the variance that we saw before by Dean and Reuschmann. It's the sum of all the dth powers of j minus the sum of the dth powers of the Hook length formula, and there's a coefficient out front. And those coefficients are the Bernoulli numbers, which pop up in lots of different situations when you have sums. So believe it or not, Matthias guessed this formula from data. He's so impressive that way. But it turned out that after we had the proof and everything, we found out that this was easy to prove, and we had to get rid of our lovely proof. So it's easy to prove because there's already a theorem that's in the literature that tells you how to find cumulants just like this in a much more general case. And this was originally, I'm crediting Chen Wang because in their 2008 paper on Q analogs of Catalan numbers, they had the core elements of the proof there, but it wasn't really noticed in general until Wang and Zakharovich saw it in 2015. So they said, anytime you have like a Q analog of a Hook length formula like thing, so you have a numerator that's a product of Q numbers and you have a denominator of the same size product of Q numbers, if it happens to be that that rational product is a polynomial with non-negative integer coefficients, which is very special, right? If that happens, then you do get a random variable that goes with it, and the cumulants for that random variable are always sums of the dth powers of the numerator numbers minus the sums of the dth power of the denominator numbers, times this Bernoulli number out in front, b sub d over d. So, okay, well, once we saw this theorem, we're like, oh, well, that's good. That at least it makes writing the paper easier. But we just think that this is the coolest formula, and we've really been digging into where else does this apply. And I hope that's what the takeaway message is. Anytime you have a formula like that in your work. So Ben, as you mentioned, like for a lot of Hilbert series, you get factorization like this. You know, when do we get some nice cumulants? When do we get asymptotic normalities on our to-do list of things to think about? So this theorem of Chen Wang Wang and Wang Zakharovich exactly proves our formula for the Dth cumulants. And then we used that to say something, you know, about asymptotic normality. But that's sort of where we were. And I want to say something about a little bit about where we're going. We're so excited about this formula and what we can get out of it that we decided we want to pay more attention to all the formulas, all the Q analogs of the hook length formula out there that are of the form some constant times Q to a power times one of these rational generating functions with product of Q numbers divided by a product of Q numbers. And we're going to call them cyclotomic generating functions. So our next paper that's coming out is going to have this as the title. And we want to talk about all the things that we can say about this whole class of polynomials. So that's the way we would define it, the first form, rational form. You could also define it in the cyclotomic form. So these are all polynomials that have non-negative integer coefficients, and they can be written as a product of cyclotomic polynomials times factors of Q and a constant. Or another way to say it is the complex form. All of the roots of such a polynomial are either roots of unity or 0. And those three are equivalent statements. We have to prove that. Okay, so what are examples then of cyclotomic generating functions? They include, in addition to the Q hook length formula, Richard Stanley has a very nice Q analog of, I should say principal specialization of the Schur function S lambda. That's when you plug in for the variables 1, Q, Q squared, and so on. And I want to talk about that one a little more. Bjorner and Wachs have a beautiful analog of the hook length formula for cosets, which are forests. We know due to the theorem of Macaulay that Hilbert series of polynomial quotients can have this rational product form as long as you have a homogeneous system of parameters. And when you're looking at root systems and Weil groups and such, Chevrolet's formula points out that there's this length generating function restricted to minimal parabolic cosets. The length generating function often has this rational product form too. And the last one's a little bit more obscure, but in work of Iwahori and Matsumoto, and then later reproved by Stenberg-Joie, there's another length generating function that comes up in Koster group theory. And Mike Zabrocki put this name on it, it's badge minus in, but it has the same rational product structure. And that one actually we've already completely analyzed too. So the new work is really on number 1 and number 2. We wanted to say, could we also look at the asymptotics for the principal specialization of a Schur function and for these hook length formulas for forests? And they got much more difficult and interesting. So it's taken us some time, but we now have a pretty good grasp on that. And that's what I wanted to explain, at least the first one. And then I might have to leave the second one to you to look in the paper if you're interested. All right, so, and here the point is that because the Chen Wang Wang and Wang Zakharovich theorem, we'll be able to get the cumulants for all of those families of cyclotomic generating functions. Okay, so in recent progress, I put it down here. Number 1, I want to show you MacMahon's formula and counting plane partitions in a box, but really actually that's a special case of this Stanley Littlewood formula for principal specialization. And then I'm going to have to leave off the Bjorner-Wachs stuff, but all 3 of these cases come up in the new paper. I'm going to start with the MacMahon one because it's the simplest one and we have the most complete results there. And it sort of explain our philosophy by going through the simplest example. Okay, so what are plane partitions? You've probably seen these before, but this is what happens if you have a whole bunch of cubes sitting around in your office and you stack them over in the corner, right? They end up, the highest part of the stack is in the back of the corner, right? And then they go down. And you could tell somebody what your plane partition is by making a tableau and filling it with numbers, but this time the tableau would have decreasing across the rows and down the columns, weakly decreasing in both directions. So those are the plane partitions. And if we say that these are the plane partitions that fit inside A by B by C box, well, it just, you have some bounding box that you're containing them in. And that way we have a finite set of plane partitions. And MacMahon has this beautiful formula for counting the number of plane partitions of a given size. Size is just the number of boxes in your plane partition. And it is exactly one of these cyclotomic generating functions. Very nice. So it should have these nice cumulants, and we should be able to tell you in what ways could A, B, and C go off to infinity and we get asymptotic normality. That would be the goal here. And so we're going to take each of these polynomials and make a random variable out of it. So chi sub A, B, C size is the corresponding random variable. And I put the star there. I don't just want you to pay attention to the little star. That means we've standardized it. So shift it so that it's mean 0 and standard deviation 1. And then just recall the notation N01 is the standard normal. And then the Irwin-Hall distributions, that's the sum of m independent random variables that are continuous uniform on 0, 1. Okay, so with that notation in mind, then we can give you a complete characterization of asymptotic normality, or actually just convergence in general among these random variables. So let's think of, I'm getting rid of the superscripts here because they get a little more complicated. So if A, B, and C, you think of them each as sequences of positive integers. Okay, so the corresponding sequence of random variables approach normal if and only if the median of the numbers A, B, and C approach infinity. So median is the analog of aft in this case. And if the convergence goes to Irwin-Hall distribution, that's going to happen if and only if you do have convergence among A times B and it's less than infinity. And the largest one of the three has to go off to infinity. Then you get Irwin-Hall distribution. Okay, and it might be the case actually that all of your A, B, and C stabilize to a constant sequence, in which case you get just the discrete distribution again. But I wrote it like this because here we're thinking of it as what's happening to median. So focus in on median. And our philosophy, and I'm going to try to convince you that we can call this a moduli space, because I feel like it is a little bit of a leap for us algebraic combinatorialists to use that language, but it just ended up being the perfect thing for us here, and it really ended up motivating some of our theorems. So let me explain that. So we know by the central limit theorem that if you take the limit as m approaches infinity of the Irwin-Hall distributions, standardized, you'll get the normal distribution, right? And I want to claim that instead of parameterizing the Irwin-Hall distributions by the set of positive integers, we should use the reciprocals. So let's define the parameter space P sub IH for the Irwin-Hall. The parameter space there is 1 over n for all positive integers n. And what's nice about that is it has a topological structure just coming very naturally from the fact that it's sitting inside the real numbers. And what does it converge to at the bottom? It converges to 0, right? So we use that. So let's define the moduli space of Irwin-Hall distributions to be the set of standardized Irwin-Hall distributions for all m. And here we include the 0, so there's a little shift involved just to be complete. But we're going to endow this moduli space of Irwin-Hall distributions with the topology too. It's the topology of convergence and distribution, and that's well defined using the Levy metric. If you haven't seen that before, it's actually not too hard to define. It's just you look at the two different cumulative distribution functions and ask what's the size of the largest square you can inscribe between the two curves. What's the side length of such squares? That's the Levy metric. Okay, so we have this moduli space of Irwin-Hall distributions. It's parameterized by the numbers 1 over n. And the conclusions here, if you take the closure of the parameter space, the closure just includes the point 0, and that's it, right? If you take the closure of the Irwin-Hall distributions, you get the normal distribution, and that's it. That's the whole closure. And there's a bijection between these two closed spaces, and it's actually a homeomorphism. And because we have this topological structure then between the parameter space and the moduli space, this is, between the set of distributions, we think of it as a moduli space. And this was the easy example. It gets a little more complicated with the other ones. So any questions here in that philosophy?
I'm just curious, like how maybe I'm not so used to seeing this stuff, but like this metric that you use, how did that, like, was it just natural to use that metric, or?
It's pretty standard in probability theory.
Okay.
Yeah, if you look in a book on probability, convergence, and distribution kind of thing.
Okay.
There are others, actually. There's the Picard one. It gives you equivalent results. Yeah. We didn't make that up at all. Okay, so then let's talk about plane partitions. There is a moduli space of plane partition distributions. These are the ones where you take all of the random variables standardized for all possible plane partitions and sitting inside boxes A by B by C for all positive integers. And you could put a topology on that too, convergence and distribution. And the claim is that in the Levy metric, when you take the closure of that topology, you have to add in the closure of the Irwin-Hall distribution. So all the Irwin-Halls plus the normal. And that's exactly the set of limit points that you get for the plane partitions. So this is just sort of restating the theorem that I said before, but in this new moduli space language. Okay, and we actually, the old theorem that we had before, we could restate in the new language too. So there is a moduli space of standard Young distributions. And when you take the closure of that, again, you get the closure of the Irwin-Hall distributions. It's exactly, I just actually literally, to make this slide cut and paste, you know, PP versus SYT. So you get the exact same thing. And now it gets more complicated, like I said, though. These two cases were really nice. We loved this because it's complete answers. But you're always pressed with the next question. So we wanted to look at the these other formulas due to Stanley, Littlewood, Bjorner, Wachs, and so on. And so let me tell you about that. Schur polynomials and the principal specialization. So instead of standard Young tableau, let's consider semi-standard Young tableau. And this isn't too much different, but you fill a partition shape with positive integers, and now we allow them to be weakly increasing on rows, but we still require them to be strictly increasing in columns. And for each such filling, you can make a monomial. So x to the t means x1 to the number of ones that appear in t, x2 to the number of twos that appear in t, x3 to the number of threes that appear in t, and so on. So for this example, 1, 3, 3, 3, 3, we have 4 threes, so x3 appears 4 times, right? There's 1, 9, there's 1, 1, and so on. If you take the rank of this tableau, I want to call that 28. And why is that 28? That's not the degree of this monomial. It's actually what you get it'll be the degree of q to the power something. If you plug in, for x1, you plug in 1, for x2, you plug in q, for x3, you plug in q squared, and so on. Then you get q to the 23. I'm going to need that definition later on. All right. And so in general, if you have alpha 1 1s, alpha 1 2s, and so on, then the rank of a tableau is going to be I minus 1 times alpha I. That's just like that statistic we saw on partitions before. And the Schur polynomial, which is like the precursor to the Schur function, which is the infinite version, it's just the sum over all semi-standard Young tableau, where you fill the tableau of shape lambda with numbers from 1 to m. And I'll use the notation SSYT less than or equal to m of lambda for that set. Okay, and the Schur polynomial is just, it's a finite polynomial that has this form. It's on m variables. But now I kind of foreshadowed a little bit because I've already told you we want to look at the principal specialization of that polynomial. We're gonna plug in 1q, q squared, and so on for the variables. And that'll be just like taking the sum over all semi-standard Young tableau with entries less or equal to m of shape lambda and putting q to the rank of t. And Stanley proved the first formula, which is another cyclotomic generating function rational product like that, and Littlewood proved the second formula. These are both very, very nice. Once again, very efficient formulas. This makes it so easy to look at data, right? And there's a little bit of notation I should define there. C sub u is the content of a cell. So if a cell is in matrix coordinates I, j, the content is just j minus I. And H sub u is again the exact same hook length formula. You need that for Stanley's version of it. But we have these two versions and we actually use both of them to get various information about the polynomials because we get different formulas for the cumulants this way. Okay, so we have polynomials, so we make random variables out of them. So chi sub lambda m of rank is the random variable associated to this rank statistic on SSYTs. And we can then, again, write down the moduli space of semi-standard Young distributions by standardizing all of those guys and stick them all into one big set together. And we want to impose a topology on it, again, using the Levy metric. And the question is, what is the closure of that set of distributions? And this is an open problem still. We have not completely solved this. We've been attacking it and we've got ideas for it, but it's open for you to jump in. Please help us out. So we would love to understand exactly what are the limiting distributions here. But let me tell you what we have been able to do. We have found a somewhat unexplored set of distributions that come up very naturally inside of this closure. And to describe them, we have to generalize the Irwin-Hall distributions. So remember, they were also called the uniform sum distributions. So these new ones are going to be called finite generalized uniform sum distributions. And that's what you get whenever you take an independent set of uniform distributions anywhere at all, and you add them up, you get some distribution. If we standardize that thing, it won't matter if they're spread all out or not. You might as well make them all have mean 0. And so in which case, I'm going to think of them always as just sums of uniform random variables that straddle the line 0, 0, and they're symmetric. So u of t minus t over 2 to t over 2, kind of, those are the basic ones. And for any sequence of real numbers, t1 greater than or equal to t2 up to greater than or equal to tm, we could add up uniform distributions that have those bounds, and that's going to be a finite generalized uniform sum distribution. And I claim actually all of them come up in our work in limiting distributions of these generalized hook length formulas, but not all of them come up with semi-standard Young tableau. So I want to describe the ones that come up with semi-standard Young tableau as a special case. And you see how these do generalize the Irwin-Halls, right? If you just take the numbers 1, 1, 1, 1, 1, you get something that's almost Irwin-Hall distribution, just it won't have mean the same. Okay, so to get to semi-standard Young tableau, we also have to look at the distance multiset of a set. So if you have a decreasing sequence of real numbers, t1 through tm, the distance multiset is what you get when you take the m choose 2 differences, ti minus tj. Take the bigger one minus the smaller one. So these will also be non-negative real numbers. That's the distance multiset delta t. And then the theorem with Josh Swanson here in this new paper is that the generalized uniform sum distributions indexed by delta t's of this form all come up corresponding to some sequence of standard Young tableau or semi-standard Young tableau distributions. And which ones are they? They're going to be indexed by sequences of partitions where the first row grows a lot faster than the value m, the sort of the bound on the variables that we're using. So as long as lambda 1 over m cubed goes to infinity, then we're going to construct a sequence t1 through tm by just taking the fractions lambda k over lambda 1. So just divide all the parts of lambda by the largest one. So we get a bunch of numbers between 1 and 0 decreasing. And then you take the delta t, the distance multiset of those values. And as long as you have those distance multisets, as long as they converge pointwise, just in your old-fashioned real analysis sort of sense, then we have convergence in distribution of the random variables. And if those random variables, if the value m goes to infinity, we get asymptotic normality. And if m is bounded, we end up with one of these generalized uniform sum distributions. Okay, so that's kind of the analog of the story with semi-standard or with standard Young tableau and also with plane partitions. It's a little bit incomplete, right? I didn't tell you that I entirely understand the closure, but I know that these guys are in the closure. But this made us start looking then, what can we say about the moduli space of distance distributions? What if we just focus in on these generalized sum distributions that are indexed by distance multisets? And we could have a parameterizing set too. It looks a lot like, what I've written here, sort of subsets of real numbers that are decreasing starting at 1 and going down to 0. And then if you have this p dist, we claim that you take the closure of p dist, there's exactly 1 extra point in the closure, so it's like a 1-point compactification. All you have to add there is the infinite sequence of zeros. And the closure of the moduli space m dist is, once again, m dist union just the normals. Just the normal 0, 1. There's 1 extra point you have to add, 1-point compactification. Again, you have a homeomorphism between the parameter space and the moduli space of distance distributions. Okay, good. Say again?
Quick question, are this result seems very similar to the previous one. Was it similar methods used in the proof, or is it all new considering that you having
it ended up, we had to do a
persistent.
lot, for this paper, we ended up having to do a lot of work, sort of all of section 3 is devoted to understanding pointwise convergence, and how does that relate to convergence of distributions of uniform sums, these generalized uniform sums. And so it's not at all very much related to the old paper. It actually, we ended up having to do work in probability and real analysis that I never intended to do. So I have to give Josh all the credit for that, actually. It really pulled me dragging, screaming and kicking and screaming into the real analysis. And I'm glad we did it, actually. I think it's very interesting, but it was kind of surprising to us that it hadn't already been, we don't believe it's been done in the probability community before to look at these generalized uniform sums. And I was going to say, we ended up for the, I'm getting out of time, so let me just kind of cut to the chase here a little bit. So for the Bjorner-Wachs case, we had to expand our horizons a little further. We had to look at all of the generalized uniform sums and even go to countably infinite sums. They all come up. And as long as you have variance, a finite variance, all generalized uniform sum distributions can come up. So we ended up looking at the moduli space of all of those and taking its closure. And when we did that, we found that there was a little gap that had to be filled that we didn't know about. And so we had to introduce yet another new family of distributions, which are not like new in the sense that you've never heard of them, but they just haven't been studied before. And we call these the dustpan distributions. And the dustpans, they correspond to taking one of these generalized uniform distributions plus a normal. And that helped us because we needed to, it was the second cumulant. There was a little gap in the second cumulant that we needed to fill in order to find all of the limits. So that's why we just had to stick the normals in there. And it might be that you put in a normal 0, 0, which sort of means you're not adding anything. But you also can add other ones too. The dustpan nomenclature comes from, it's a distribution associated to a uniform sum plus t for a independent normal distribution. And I kind of like the idea of dustpan because, you know, these are the limit points that you get. These are like the little dust at the edges that has accumulated. So we have now the sort of the best statement that we could make is that for both standard Young Tableau, semi-standard Young Tableau, and for these Q analogs of hook length formulas that are due to Bjorner-Wachs that are associated to forests, we don't know the closure of the corresponding moduli space, but we have said that these things, a bunch of things, are included in each of the closures. So for semi-standard Young Tableau, we know that the closure of the Irwin-Halls is in there. We know that the closure of the distance distributions are in there, but we don't know what else is in there. And for forests, we know that what we ended up proving, actually, in my opinion, the key technical result is that when you take the compact closure of the dustpan distributions, you find out it's itself. It is already closed. And so we know for forests, the closure of the moduli space of forests is going to include the dustpans, but what else? And so it's again an open problem to describe that in the Levy metric. What are all the possible limit points for the moduli space of forests? And an interesting fact is the semi-standard Young Tableau, standard Young Tableau case are not unimodal. Remember I mentioned that? But for the forest distributions, they are all unimodal. So the M forest closure is not even all possible distributions that come up if you look at cyclotomic generating functions. So there's an even bigger open problem. What is the closure of the moduli space of cyclotomic generating function distributions? And so I would claim that is the moduli space of Q hook length formulas that we are really looking for. And so that's where we're going. All right, any questions? Here, I'm gonna send at you a little bit of Seattle since I can't be there with you.
Awesome, let's thank Sara. Are there any questions?
I have a question. It's really more about some of the earlier stuff, but is there some naturally arising Markov chain that samples from the major index distribution on standard Young Tableau? Like not cooked up with Metropolis Hastings, but like some really, you know, straightforward to describe process. This, I mean, I don't know that much about probabilities, so this might be.
Well, I guess one Markov process you could put it in there is with that poset structure that we gave. right? And we do have some natural ways to go from one to another. I don't have a good way to describe how many tableaux are attached, like how many elements are covered by one. I don't know that at all. We give a very explicit definition of the covering relations for both of those posets.
Okay.
Yeah, but that might be interesting. I mean, you might want to be able to move around on that tableau in both directions, right? And see where do you end up, where do you converge to? It's a good. Could be a good question. I don't know. I don't quite understand like the movement.
That's what I was wondering too. I mean, if you can draw uniformly, then you can potentially just adjust by the, the value that you can compute. But if you actually wanted to sample without knowing that ahead of time.
Right. Right.
I have to scoot to another meeting, but thank you. That was awesome.
Thanks, Ben.
Are there any other questions? I guess I'm just curious if you have some feeling of how doing this same stuff for the other examples that you put on the list that you didn't touch on, how messy does that get?
I'm actually hoping they're easier.
Okay.
Because forests were really hard, in terms of what it pushed us to do. I actually think that Hilbert sequences are going to be nicer, and also the Chevrolet formulas are a little bit nicer. But I don't know exactly like which cyclotomic generating functions can be realized by a Hilbert series for some quotient. It's another big question in my mind.
Awesome. Are there any other questions? If there are not, let me just remind you that next week we're just down to our last two discrete CATS seminar talks for the semester. Next week, Dr. Ehrenborg will be talking to us about 3 combinatorial applications. So there are 3 kind of, I guess, Dr. Ehrenborg, the 3 different topics. So in one talk.
It's really 3 small talks put together into one.
Sounds good. Yeah. So hopefully you all can join us next week. But if nothing else, let's thank Sara one more time.
Thank you, everybody.